My dear friends, today I'm going to explain the diamagnetisms. Diamagnetisms. Diamagnetisms mean those materials which are feebly repelled. Feebly I mean weak. Feebly repelled by the magnet. Mean those material they opposes to magnetic field. Now let's come in the reason why the diamagnetic material they oppose to external magnetic field. Okay. Before going to discuss the reason of the diamagnetisms, so friends, you know very well about like if I'm having a circle, this circle, and electron is orbiting. Let I think electron is orbiting, in this direction. This is anti-clockwise. And you know very well the direction of the current. It is other way around. If electron is orbiting anti-clockwise, then current direction will be clockwise. Fine. Mean current is along the clockwise direction. Now you know very well when the current circulates, then this loop behaves like a magnetic dipole. It becomes a magnet, tiny magnet, having North Pole and South Pole. And remember, like N, okay, N mean put the arrow like this. So this circulation is anti-clockwise. So anti-clockwise behaves like a North Pole. And put the arrow. So this is clockwise circulation. Clockwise circulation behaves like a South Pole. So you know the upper phase, the current is clockwise. So upper phase will behave like a South Pole, and the lower phase of the same loop then will behave like a North Pole. Okay, that means it is like a tiny magnet. If it is a tiny magnet, it must have magnetic moment, because magnetic moment tells about how the magnet is strong. Well, the strength of the magnet. Magnetic moment tells the strength of the magnet. And you know the formula of the magnetic moment is current multiplied by area. You know current is charge over time. So very well about angular velocity. What is angular velocity? There's 2 pi upon t, angle over time. And from here the time period is 2 pi by omega. So substituting t here, so magnetic moment becomes charge divided by what? 2 pi by omega. Omega comes in the numerator multiplied by the area. Area of a circle is pi r square. This is a magnetic moment when the electron orbits in a circle, it behaves like a tiny magnet and having magnetic moment. Now, magnetic moment is a vector quantity. Now, what about the direction of the magnetic moment? You know, apply the right hand thumbs rule. If you curl your fingers, the curl your fingers, it shows anti-clockwise. Then thumb will be upward. Then the magnetic moment will be upward in direction. But in our case, current is clockwise. Clockwise current means the thumb goes inward into the paper. Okay? If it is current is anti-clockwise, it is out towards the reader, mean out to the paper or towards the reader. If the current is clockwise, curl your finger, it is clockwise, the direction of the magnetic moment will be, away from the reader or into the paper. Into the paper or away from the reader. So that means magnetic moment will be along this direction. Along this direction. This is the direction of magnetic moment m vector. Current decides the direction of the magnetic moment. Of course, the current is not a vector quantity, but when current multiplied by the area, then it becomes magnetic moment becomes a vector, and direction of the magnetic moment then decided by the direction of the current in that area. Okay, in an area of cross section, this area. So in our case, magnetic moment is into the paper, away from the reader. Now substituting the value of area, magnetic moment becomes E omega upon 2 pi r square. Dear friends, now I am going to explain the reason of the diamagnetism. Let's suppose that I am having an atom in which two electrons are circulating. One electron is circulating anti-clockwise, and in that case current will be along the clockwise in direction. In second electron, second electron it is circulating clockwise, but in that case current will be anti-clockwise. And you know very well, I just explained to you what is the formula of the magnetic moment. E omega r squared divided by 2. Omega is the angular velocity. More the angular velocity, more will be the magnetic moment. Magnetic moment means the circulating current in a loop behaves like a magnet. Okay? And the strength of that magnet is by the magnetic moment. And you know very well, if current is anti-clockwise, that will be the north pole. If current is clockwise, that will be the south pole. So here here clockwise, Clockwise means the upper phase behaves like a south pole and lower phase behaves like a north pole. Here the current is anti-clockwise. Anti-clockwise means north pole and south pole. North-south means this loop behaves in which current is circulating. And of course the radius is the same because circle is same. And magnetic moment in magnitude will be also the same. Now there are two magnetic moments. One for this, one for this. South-north, north-south. They cancel out. They cancel out. Then there is no net magnetic moment in this case. When there are two electrons, they are orbiting one clockwise, other anti-clockwise. Both are having magnetic moments, but they cancels out. So north cancels, north-south cancels. Okay. Now in this case, because the current is, like anti-clockwise, the moment will be along up direction. So there are two magnetic moments, one downward, second upward, same magnitudes, opposite directions, cancels out. Now next, I'm going to apply a magnetic field. Magnetic field like external magnetic field, north pole, and here the south pole. This is the external field. Okay, north to south. Mean the direction of field will be, this is the direction of the external field. Be external. Now what will happen? If this is the external field B vector, what will be the role of B vector? Now a formula that force is equals to Q V vector cross B vector. Mean if there is a charge circulating with velocity V in a magnetic field P, will experience a force F. That means this current which is clockwise, it will experience a force. This current which is anti-clockwise, it will also experience a force. Now problem is, what about the direction of the force on this current? You apply the Fleming's left-hand rule. Now what is left-hand rule? Now this pencils is a magnetic field. This pencils the current. Okay, this pencil force. Magnetic field, current, then force. Okay. Now magnetic field is upward. Now I apply it here. The current is in clockwise in direction. So I turn it like this. So magnetic field is upward direction. This is the direction of the current, and this will be the direction of the force. Okay, magnetic field upward, current like this, force will be along this span. Mean this current will experience a force along this direction. So if it will experience a force along this direction, again look. Okay, magnetic field, current, then force. Force will be along the radius. So, like this is the magnetic field and direction of the current direction of the force. Mean Fleming left hand rule like this. Okay. So what will happen? This force, it favors to centripetal force because centripetal force is always towards the center of the circle. That means magnetic force is in favor to centripetal force. When this force increases, it will in turn increase to the velocity of the electron. When velocity increases, mean omega increases. When omega increases, mean magnetic moment increases. So magnetic moment increases, becomes m plus delta m. Delta m is the change in the magnetic moment because of the external applied field, which is along up direction. So this magnetic moment increases. I've shown it with this length of the line. Now I will show it with bigger length of the line because it is now m plus delta m. Now coming to this case. Here, now here there is also magnetic field external B vector. Current is, here anti-clockwise. Now applying the same rule. Look, magnetic field, okay, current and force. It is away from the radius of the circle, like here. Okay, magnetic field, current and the force, like this, right? So the force will be along this direction. Now this force, it is in opposite direction to the centripetal force. So what happened? The centripetal force get reduced. With the reduction of the centripetal force, this velocity decreases because the centripetal force is equals to mv square upon r. If F decreases, the velocity decreases. So with decrease in centripetal force, V decreases. Okay, decrease in V mean omega decreases. Decrease in omega mean magnetic moment decreases. Magnetic moment, which was along up direction and it was m, now it gets reduced. It becomes m minus delta m. Now I will show it with the smaller line. Now the net moment here with the application of external magnetic moment, with the application of the external magnetic field, now the magnetic moment turns to m minus delta m. In that case where the current is anti-clockwise and magnetic field is along the up direction, mean towards the reader. Now in this case, where the current is clockwise and magnetic field is along, it is in the up direction, mean towards the reader, the field is towards the reader. Here the magnetic moment increases, here the magnetic moment decreases. Now what the net result? Now two moments, now they will not cancel out because they are of different magnitudes. This moment is greater, it is lesser. What the net magnetic moment? Net magnetic moment left, they are not cancels now. Net magnetic moments left m plus delta m minus m minus delta m. So what happened? It becomes 2 delta m. So we are having 2 delta m net magnetic moment. Will you tell me what will be the direction of the net magnetic moment? Definitely you will say where it was a bigger line. So this is the bigger line of the magnetic moment. So net magnetic moment becomes along this direction 2 delta m. And just notice this net magnetic moment, it is in opposite to the external magnetic field. That's the reason this atom in which two electrons are orbiting, it will oppose to the external magnetic field with magnetic moment 2 delta m. So this is a general case which shows if you are having even electrons in atoms, in the absence of the field, the magnetic moment will cancel out. But if you apply the external magnetic field, those atoms will oppose to the external field. So this is all. I think if anything is not clear, please tell me in writing in the description box. Okay? Thank you.